Today I would like to talk about singularity categories and Calabi-Yau structures. So the subject is, so I will be interested in singularity categories. Which are Calabi-Yau. Yes. And yes, Calabi-Yau property is a property of triangulated categories. And so what about Calabi-Yau structures? Well, it is more or less. Yes, so roughly speaking, the Calabi-Yau structure is enhancement of these Calabi-Yau properties of triangulated categories to DG categories. To lead to differential graded enhancements. So in the two talks, I would like to first start from some background on Calabi-Yau triangulated categories and also some brief background on DG categories. And then I would like to discuss two classes of Calabi-Yau triangulated categories. And the first one is about commutative algebras, the singularity categories of commutative algebras. And the second one is about singularity categories of some finite dimensional algebras. And this first part is based on joint work with Samuyama. And the second part will be based on joint work with Bernhard Keller. So yeah, let me start from the first background part. And so I will start the discussion with some basic definitions around Calabi-Yau triangulated categories. So, yes. So throughout, I will fix a base field K, which I assume to be perfect for simplicity. And the definition is, yes, so let T be a K-linear triangulated category. So the first of all, the cell functor on a triangulated category T is an autoequivalence. Which are denoted by nu on this category T, such that we have the cell duality. Yes, namely the duality between the home spaces from X to Y and from Y to nu X in a functorial way. Yes. And for each integer n, T is called n Calabi-Yau. If the n suspension functor, which are denoted by n shift, bracket n, is a cell functor. So it means that we have this duality formula with the n shift in place of this, this nu. So we are required to have this kind of X symmetry triangulated category. Yes, so the first example, let A be a finite dimensional Iwanaga-Gorenstein algebra, or just simply Gorenstein. In the sense that, in the ordinary sense, namely, it has finite injective dimension on each side. And then its perfect derived category has a cell functor given by the tensoring the injective module. Yes, so the derived Nakayama functor. Yes, it is a cell functor. Yeah, which can be shown in a very elementary and formal computation. And so what about example of Calabi-Yau triangulated categories? Well, it originates in the Calabi-Yau varieties. So if X is a, let's say, smooth and proper Calabi-Yau variety of dimension n, in the sense that the canonical bundle is trivial, then the derived category of coherent sheaves over X is a n Calabi-Yau as a triangulated category. And yes, this explains this terminology, Calabi-Yau. And in representation theory, one of the classical examples comes from commutative algebra, namely let R M be a commutative Gorenstein isolated singularity. So which means that for any non-maximal prime ideal, the localization is regular. Then a classical Auslander-Reiten duality implies that the singularity category, which I would denote by SGR, is so as in the previous talk, it is the Deodale quotient of bounded derived category by the perfect derived category is dimension -1 Calabi-Yau as a triangulated category. And also more recent example comes from pre-projective algebra. So let Q be a finite acyclic quiver. And let lambda be the pre-projective algebra of Q. So what are they? So if we have a quiver like this, we can, from a quiver like this, we consider the double of Q. So we add, for each arrow, we add an dual arrow to the opposite direction. And and consider the path algebra of this double quiver modulo the ideal generated by the commutators. Yes. And this is the pre-projective algebra. And then if Q is thinking, then this pre-projective algebra lambda is a finite dimensional, and its singularity category is a 2 Calabi-Yau triangulated category. And if Q is non-Dynkin, then we have another 2 Calabi-Yau triangulated category, namely the derived category of finite length module over lambda is a 2 Calabi-Yau triangulated category. Yes. So depending on whether or not Q is thinking, we have somehow different kinds of two Calabi-Yau triangulated categories, and one of the goals of my talk is to explain how these differences appear and what are the corresponding objects and so on. And yeah, that will be one of my goals. And yes, maybe I should say that if you already know what derived pre-projective algebra, the DG version of pre-projective algebra, you might know some of the answers. Yes, why this is to Calabi-Yau, and yeah, that's part of my answer, but not the whole part of my answer. So yeah, I think I can give you some new information about this. Yes. Okay, so this is the first thing about Calabi-Yau triangulated categories, and next I will like to explain some background about differential graded categories. And which I think will be also relevant to lecture series by Xiaowu Chen, but anyway. So differential graded will be abbreviated DG categories. So what are DG categories? So, and the shortest definition is that it is a category enriched in complexes. So it has, as in the case of ordinary categories, it has, let's say a DG category A. A has objects, and instead of ordinary morphism set, we have morphism complexes. Noted AXY. And so what does enrichment mean? So it means that the composite has to be a morphism of complexes. Yes, composite. Sorry, X to Z has to be morphism complexes. So which means that it should commute with a differentials of this thing and this thing. So if you remember the differential of the tensor product of complexes, it is d plus 1 plus 1 plus d. So if you write this commutativity down, then it will become like this. So a differential of the composite should be dg circle f plus minus 1 of degree of g times g circle df. So it is nothing but the Leibniz rule. Okay, so this is DG category, and let me give one most fundamental example. Is that if we have a base field denoted by CDGK, the DG category of K vector spaces. So it has objects are the same. Yes, complexes of K vector spaces. And morphism spaces are, morphism complexes are given by Hom complexes. So it has, it is denoted by curly Hom, whose degree n part is the map of, degree, the graded map of degree n. And the differential takes this degree n morphisms to the composite with each of the differentials. Yes. Yes, I think you have seen this formula before, but yes, and this is the most fundamental example of DJ category. And another important example is the DJ algebra. Yes, DJ algebra is a DJ category with single object. And even more, even more simple example is just an ordinary algebra. Yes, an ordinary algebra is a DG algebra concentrated in degree 0. DG. Degree 0. Yes. And the well-known slogan is that these DG categories is an enhancement of triangulated categories. So what does it mean? So if we have a DG category, what we can do is to replace each morphism complexes by its cohomology. Yes, yes, we can think about H0 of A by replacing by keeping the objects and replacing the morphism, each morphism complex by its cohomology. Yes, for example, we can think about, let's consider a finite dimensional, let's say a finite dimensional algebra. Yes, it doesn't have to be finite dimensional. Let's say a Noetherian ring. And let's consider the category which are denoted by C, B, D, G, proj A, which is whose objects are bounded complexes of finitely generated projective A modules and morphism complexes are home complexes over A. Yes, yes. So we have A module on each component, so we can think about the home complexes over A, and which form a DG category. Yes. Then so what would this H0A become? Yes, if you look at this formula closely, yes, so this for morphism F in degree 0, morphism F to be in the co-cycle means that it should commute with the differential. And for degree 0 morphism to be in co-boundary means that it is precisely the no homotopic ones. So as a H0 category, what we get is nothing but the homotopy category. Yes. And which is equivalent to the perfect derived category of A. Yes. And in this way, we can realize this triangulated category as a H0 of some DG category. And in this sense, yes, this DG category is called the enhancement of this triangulated category. And similarly, we can do something. We can do something similar, but with several other boundedness conditions. Yes. So we consider the C minus B DG approach A, whose objects are bounded complexes of finitely generated projective A modules with bounded cohomology. And if we do something similar, we get is as H0 is the corresponding homotopy category, which is equivalent to the bounded derived category of A. And in this way, we obtain the enhancement of bounded derived category. Yes. So So these kind of examples suggest that what should the enhancement of our Calabi-Yau property of triangulated category should be? Yes. So let me define that notion. Yes, so okay. Definition is that let's say I will intentionally leave some space here and an n Calabi-Yau structure on a DG category C is a natural isomorphism C of xy and C of yx shifted by n dual. So yes, so this is a naive definition, but we shouldn't require this to be a strict isomorphism on complexes, but just the isomorphism in the derived category. Yes. Yeah, in other words, it is just required, we should just require to be a quasi-isomorphism. And in other words, if we drop this object, it can be written as a dual of C, isomorphic to C shifted by n in the derived category of bimodules over C. Yes. And in this case, the perfect derived category of C, which is the triangulated category that C enhances, that is an n Calabi-Yau triangulated category. Okay, so I will add some comment on this definition. It is precisely called the yes, right Calabi-Yau structure. And it is moreover, we should say it's more precisely, it is a weak right Calabi-Yau structure. Yes, so I would like to make some brief comment about this definition. So yeah, as I said, it is an isomorphism in of bimodules over C. So it lives in the space where from C to shifted by n to dc in the derived category of bimodules. And by adjunction, this is which one is it? A minus n cohomology of yes, a dual of C derived tensor C of C, and which is nothing but the dual of the Hochschild homology of C. Yes. Yes. So this is the this is an invariant that of a DG category that this isomorphism lives in. But from the point of view of deformation theory, we should require something stronger. And in fact, the correct definition is said to be that, yes, we have a natural map from the dual of the cyclic homology of C. And this is, and yeah, we should require the isomorphism should come from an element here. And that is what is called the genuine Calabi-Yau structure. Yes, right, Calabi-Yau structure. And its image would be something called a weak right Calabi-Yau structure. Yes. Okay, so the precise definition is the element in here, but today I will not want to go into the detail of this. So today I will just call think about this isomorphism here. Yes, today call such C right and Calabi-Yau. Yes. Okay. This is the definition of the Calabi-Yau property for DG categories. Yes. Okay, so I can now go into the first main part about commutative algebras. Okay, so I will start from a commutative Gorenstein ring. Of dimension D. And I will look at not just commutative algebra, but slightly non-commutative version, namely I will discuss symmetric order. So it appeared in the previous talk, but to briefly recall what it was. So lambda is an R algebra, which is finitely generated, and Cohen Macaulay as an R module. And if we take so this is order, and what is symmetric, we require that R dual of lambda should be isomorphic to R as a bimodule over lambda. Okay, so for example, we can take just lambda to be simply R. It is also this is one of important examples. And if we take, for example, R to be just a base field, then lambda is a finite dimensional symmetric algebra. Okay, so I haven't talked about examples in it at all, so let me give some recipe to construct Gorenstein rings. So one can produce commutative Gorenstein rings by dividing something regular. Yes. Let me be precise. So first example is if we have a polynomial ring in d+1 variables and some non-zero element, then its ideal quotient is Gorenstein of dimension d. So this belongs to a much nicer subclass called hypersurface. And secondly, if we can divide in by some group action, yes, we have some regular polynomial ring and consider a finite subgroup of SLD on which and G acts on this polynomial ring by a linear change of variables. And if a characteristic is not bad, then this invariant subring will be Gorenstein. And yeah, in particular in dimension 2, this is nothing but the simple ADE singularity. Yeah. And this is a classical result due to Keiichi Watanabe in around 1970. And we can also think about quotient, not only by finite subgroup, but by some linear algebraic group like the torus. Yes, and I would like to mention some examples. So let's consider some polynomials, some polynomial rings. Yes, in several variables, some copies, and we give a grading on each variable. A positive grading. And then we look at the Segre product. Denoted in this symbol, which is by definition the tensor product of each degree component. Yes, we look at each degree component and take the tensor product and take the direct sum of along all these integers now. And this is isomorphic to it can be seen that this is isomorphic to some torus invariant of the tensor product, yes, whose action is given by these weights. Mm-hmm. And if this sum of these weights are equal for, yes, if we for each polynomial ring, for each I, we consider the sum of weights. And if it is common for all I, then this Segre product, which are denoted by R, will be Gorenstein. Yes. 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 So the easiest example would be some polynomial ring in two copies of polynomial ring and give everything degree 1. So this is the sum of weight is both 2. So it is the Segre product to be Gorenstein, and we can, yeah, in this case we can directly compute this ring as as the generator would be yes, we collect some elements from the same degree, yes, xu and xv, and yu and yv, and these are generators. And if we set these generators to be a, b, c, d, we have one relation, namely AD and BC are both x, y, v. So it is given by one equation. Yes. So in this case, this happens to be a hypersurface. Mm-hmm. And this is called something called a 3-dimensional A1 singularity. Yes. So yes, one good point about this construction is that we can perform some very explicit computation using only the knowledge of the polynomial ring. More precisely, only using Cauchy complexes, we can perform very explicit computation, and this is one of fun points about this construction. Yeah. Anyway, these are one examples, and yeah, there are plenty of commutative Gorenstein rings which can be obtained in this way. Yes. Okay, so I wanted to talk about DG enhancement of singularity categories. So let me give a brief account of it. So DG singularity categories. So recall that the singularity category of Noetherian ring is defined as the Verdier quotient of the bounded derived category by the perfect derived category. And we had enhancements of these derived categories. Yes, so this perfect derived category was enhanced by CBDG proj lambda. And this bounded derived category was enhanced by C minus B DG proj of lambda. And the natural question is that whether we can enhance this Verdier quotient construction to DG categories, and the answer is happily yes, which is given by Bernhard Keller and Drinfeld. Yes. So for any DG categories, inclusion of DG categories can be like this. There is there's a DG functor from this such that in the triangulated category level, yes, we consider the perfect derived category and perfect derived category of C. This DG functor induces this Verdier quotient of and this in such a way this commutative. And moreover, this DG functor is unique in a certain homotopical sense. Yes, and call this C the DG quotient of B by A, and write it by B modulo A. Yes. And so by this theorem, we can, it is clear that we have this some enhancement of the singularity category. Yes, so for an Noetherian ring, the DG singularity category, the DG singularity category is defined as the DG quotient of C minus B proj modulo CB DG proj. And it is denoted, I will denote it by SG DG of A. Yes. Okay, so it is good that this enhancement exists, but the problem is, of course, how does it look like and how to understand this? And yes, there are several answers to this question, like the one given by Drinfeld, like, for example, by adding the -1 loop to its the objects from A to, so that its differential of this is the identity of this the object we want to kill. And that's one description of the DG quotient. But today, for our purpose, we want to give some description of this DG quotient in some that gives some relative understanding of this category. Yes, let me write it down. Yes, we want to understand the structure of the DG singularity category in a relative sense, relatively. And this is somehow the original definition due to Keller. And yes, this is summarized in the following proposition. In the morphism complex. Yes, let's consider the objects in the bounded derived category of a Noetherian ring A. Then the morphism complex of the DG singularity category, I will denote it by C, fits into a triangle and tensor A R home from M to A, R home A to Mn, and Cmn. Yes. Yes. Okay, this is the proposition. So what does it say? So we have this natural map we often use. Yes. For example, we often claim that there's a natural map, and this is an isomorphism whenever, for example, M is perfect. And this is far from being an isomorphism in general. So the question is, how far is it from being isomorphism, or in other words, what is the mapping cone of this natural map? And the answer is very simple, and the mapping cone is given by the morphism complex of the DG singularity category. Yes. And yes, and one remark that helps you believe this proposition is that one can easily check that for Iwanaga-Gorenstein algebra, A is Iwanaga-Gorenstein and Mn and R Cohen-Macaulay modules, then this mapping cone of this morphism has correct cohomologies. Yes, so we can show that. Then let me write it here. Then it is, one can directly show that, let's call it phi, hi of cone of phi is something as desired, namely the stable home between M from N shifted by I. Yes, this is an easy exercise. Yes, and now let me state our first main result with Samiyama HI. And so consider the commutative Gorenstein ring. Of dimension D and R a symmetrical order. And then for and we consider the DG singularity category of this symmetric order lambda. Then for each objects in the DG singularity category, we have that, yes, we consider the home complex and take the dual over R. And this would be isomorphic to C of NM shifted by -1 naturally in the derived category of R. Yes, both has R action, and this is an isomorphism of complexes of R modules. Or in, yes, if we drop this object and write it in the bimodules way, we can say the home. Our home from C to R is isomorphic to C shifted by -1 in the derived category of bimodules over. And corollary. Yes, so we have this R duo, but it's a bit different from, might look a bit different from what we wanted to show this. So yeah, so this D is K duo. Yes, so it's a bit different, might look a bit different, but if we assume that lambda is an isolated singularity, we can replace this R duo by the K duo. Yes, so corollary, if lambda has only an isolated singularity, then it is somehow elementary facts about commutative algebra that this R duo coincides with K duo shifted by minus D on finite length modules. So using this this fact, then we can replace this R duo by D shifted by minus D. So it becomes D C shifted by minus D isomorphic to C in the derived category of pi modules. And therefore, C shifted by minus 1. And so if we take this D to the opposite side, therefore, this C is right D minus 1 Calabi-Yau. So in this way, we have lifted the Calabi-Yau property of triangulated categories to DG enhancements. And one remark is that, yes, so this is a corollary for isolated singularities. And yeah, we did not assume anything about singular locus in this setting. So yeah, so in this sense, this this isomorphism over this duality over R can be seen as, yes, the theorem can be seen as certain standard duality for non-isolated singularities can be as an AR duality, or yeah, let's say arbitrary singular locus. And yes, I don't think, yeah, yes. So for example, yeah, taking the cohomology of this, taking the cohomology of this isomorphism reduces to the ordinary duality in the singularity category, but taking the zeroth cohomology of this isomorphism only yields certain spectral sequence and not so easy way, in not so, well, yeah, somehow simple way of describing the duality in the triangulated category level. So I think this is this kind of duality can be only stated in the language of of DG categories. Yes. So I think I think my time is just up. So yeah, I would like to stop my first talk at this moment. Yes, thank you very much.
Thank you very much. Are there any questions?
Hello, I might have a question.
Yes.
So in your theorem, how essential it is that R is a Gorenstein ring? Can we take it as a common local ring and lambda to be a Gorenstein order and get something similar, maybe?
So I'm not sure about well,
At least with
Gorenstein.
isolated singularities.
Yes, but I'm not sure about Gorenstein order over non-Gorenstein rings, but yes, but yeah, for example, if you consider R to be non-Gorenstein and lambda to be itself, then the singularity category in general have very large morphism spaces, not finitely generated over R. So I don't think this kind of duality cannot hold, I think.
Okay, thank you.
More questions? It seems that it's not the case. So